The second topic of chapter 3 is Bayes' theorem. Bayes' theorem is also called Bayes' rule. By definition, let's look at it first. Suppose events A1 through AN are disjoint, and the union of the n events is the sample space. So this is similar to the partition idea that we talked about in the previous video, that we are looking at disjoint events A1 through AN, and their union covers the entire sample space. And specifically, we're looking at positive probability of each of the AI events. Then for any event B with positive probability, we have a Bayes rule that can help us to get the conditional probability of AI given B. So the formula looks a little complicated, but if we look at it one by one, the items one by one is not that bad. If you look at the numerator, by the definition of joint probability, conditional probability, or marginal probability, we know that the numerator actually is AI intersection B, right? And then if you look at the generic term that we put down in the denominator, this is the AJ intersection B, okay? And in fact, if you look at the second line here, what we're doing is we're summing over all of the joint probability. So this is probably joint A1 and B. The last one is joint AN and B. Okay? So from the law of total probability we covered before, we know that the denominator will just become the probability of B, which is the marginal probability. And in fact, we know that AI given B will just be the joint of these two over the marginal. Okay? So what Bayes' rule is helping us is once you have disjoint events A1 through AN and their union is the sample space, we can get the conditional probability of any of the AI given the event B from the formula here. Specifically, we call a probability of AI is typically called the prior probability, which we're going to cover later. And AI given B is called the posterior probability. So prior is like you haven't seen anything about B yet. And then posterior is after you have seen B, what do you think about AI? So just to give you an example, and we'll work it through in class. Suppose Vassar has only 3 possible majors, math, music, and econ, and we have 25% of students in math, 55 in music, and rest are econ. And we are counting that there's no double majors here. Kemper's folklore says that 90% of the math major wants to go on dates compared with 50% of music and 10% of the econ. Suppose your roommate meets someone at an event and gets a date. What's the probability that she's dating a math major? So this is the question. Again, as you can see, that we can define A1, A2, and A3 as the 3 different majors, and we know that we assume no double majors, so they're disjoint, and we assume that there are no other possible majors, so this is a partition. So the question now is, well, conditioning the question here is, well, conditioning that your roommate gets a date, what's the probability that this is a math major? So the question is given here for you, and take your time to solve it, and good luck.